topic for our discussion for today's class is inductance of a three-phase double circuit line when it is arranged in a unsymmetrical fashion. So we have seen in the last class how the unsymmetrical arrangement looks like. If all the if all the conductors of three phases are arranged one above the other, then we can call it as a vertical arrangement. A vertically arranged conductors can be called as unsymmetrically arranged conductors, right? Now, why we are calling it as a double circuit line? Here, each phase is divided into two parts, and we are allowing one part on each side of the supporting tower. You have a supporting tower here. At one side, you are allowing one part, and at another side, you are allowing another part. So, we are calling it as a double circuit line. Now, see, as the conductors are arranged in an unsymmetrical fashion, we need to do transposition. Is it right? So, transposition is nothing but cyclic interchange. You know this already. So, what we are doing actually here is transposition. The meaning of transposition is it is the cyclic interchange of three-phase conductors at regular intervals. What is the regular interval which we are following? L by 3 distance is the regular intervals. For the first L by 3 distance, we allow the conductors as it is. First A phase, then B, then C, and here at the extremely opposite corners, we place the second part of the A phase. So, A dash, B dash and C dash. So, these are the particular distances which are given. Directly these distances are given, but in numerical problems, they will give only the vertical distances and the horizontal distance. You need to find Q by considering this as the right angle triangle and considering it as the hypotenuse. Similarly, this distance also. You need to find these two distances in the numerical problems. When you know horizontal and vertical distances, you can automatically find them. But for our derivation, we are directly mentioning it as the distance Q and the distance S, right? So, this is for the first L by 3 distance. Next, for the second L by 3 distance, when you recall your transposition cycle, which we have covered in the previous classes, so A is moved to B position. So, here you will have A, and B is moved to C position. So, you will have B here, and C is again moved to A position. Similarly, here A dash is moved to B dash position. So, you have A dash here, and B dash is moved to C dash position. So, you have C dash here, and C dash is moved to A dash position. So, you have C dash here. Like that, for the third L by 3 distance, again A is moved to B position. So, A will be here, B is moved to C position. So, B here, and C is moved to A position. So, C here. Similarly, for the second side, you will have the positions of A dash, B dash, C dash like this, as shown in this third figure. So, for the first L by 3 distance, this is the arrangement of conductors, and for the second L by 3 distance, this is the arrangement, and for third L by 3 distance, this is the arrangement. This complete process is called a complete transposition cycle. This is 1/3 of the transposition cycle. Okay, this is the second part of the transposition cycle, and this is the third part of transposition cycle. And we need to keep in mind these facts, right? As A and A dash are connected parallelly in between the sending end and receiving end, and A and A dash are the same sized conductors, the current flowing through each conductor is half of the total current. So, IA is equal to IA dash is equal to IA by 2. Similarly, this relation and this relation. Why we got these relations? Because each and every phase is divided into two parts. So, the current will also be divided into two parts. One part will flow through this conductor and another part will flow through this conductor. Similarly, for B, B dash, C, C dash. This is the one thing which we need to keep in our mind. In addition to that, we are supplying or we are exciting the transmission lines with a balanced supply. So, The sum of all the currents is equal to 0. So these are the things which we need to keep in our mind before going for derivation, right? The first method which we apply here is the flux linkage method. What is the first method? Flux linkage method. Let me go to that method. See, we as we have done in the previous class also, we have solved this inductance problem by using flux linkage method as well as GMD and GMR method. And here also we are using flux linkage method as well as GMD and GMR method. Flux linkage method is nothing but taking the flux linkage of conductor. See, for the first L by 3 distance, I am separating this diagram into 3 parts. This is for first L by 3, second L by 3, third L by 3. So, for each and every 1/3 distance, I am finding the flux linkage of the conductor A, not phase A, of the conductor A in a group containing all the 6 conductors A, B, C, A dash, B dash, C dash. So, I am now writing the expression for the flux linkage of the conductor A in a group of conductors A, B, C, A dash, B dash and C dash. So, totally you will get 6 terms. Why 6 terms? Because the flux linkage of A due to the current flowing through A itself, the flux linkage of A due to current flowing through B, the flux linkage of A due to current flowing through C, like that for the remaining 3. Now, what is the first distance? First distance from A to A distance, right? So, I am repeating again and again the concept which is called as flux linkage of one conductor in a group of conductors is very, very important, because it is used everywhere in finding the inductance, right? What is the first term? In the first term, the current flowing through this A conductor is IA by 2, half of the phase current. And what is this distance? R dash. Why it is R dash? It is the distance from A to A. Considering the internal flux linkages, we will get R dash here. Next, distance from B to A. Is it right? First I consider this, next this. Next I will consider B and B dash. Next I will consider C and C dash. So first we will start with A. A distance, A to A distance is R dash. So we will get ln of 1 by R dash. Next, what is A dash to A distance? It is mentioned here as S. So you will get ln of 1 by S. Similarly, A completed, then B. B to A distance is D. So IB by 2 into ln of 1 by D. Next, B dash. B dash to A distance is Q. So IB by 2 into ln of 1 by Q. B is completed. Now we need to go for C. Now what is C to A distance? C to A distance is D plus D, 2D. That is the reason why we got ln of 1 by 2D. Next, from C dash to A distance. What is the distance between C dash to A? C dash and A? P. So it is ln of 1 by P. Now you got 6 terms, and each 2 terms will have one thing as common. What is that? IA by 2 and IA by 2. So I took IA by 2 as common. It is like ln of A and it is like ln of B. So ln of A plus ln of B is ln of AB. So natural logarithm of 1 by S R dash, because you have 1 by S, 1 by R dash. So 1 into 1, 1, S into R dash is S R dash. Similarly, for the second and third terms, for the third and fourth terms, you got 1 by D and 1 by Q. So 1 by QD. Next, for the fifth and sixth terms, you have 1 by 2D and 1 by P. So you will get 1 by 2dP. This is the flux linkage of the conductor A in a group of A, B, C, A dash, B dash and C dash for the first L by 3 distance. So that is the reason why I represented this as lambda A1, right? Next, I will go to the second part, means second L by 3 distance. For the second L by 3 distance, see here, for the first L by 3 distance, A is here Next, for the second L by 3 distance, A will be moved to here, B will be moved to here, C will be moved to here. You can observe this here. Similarly, for the first L by 3 distance, this is the arrangement. So, A dash will move to here, B dash will move to here, C dash will move to here. So, like this you will get the distance, you will get the positions, but the distances will not change. Okay. So, this is the biggest mistake that many students are doing while considering the transposition cycle. You must change only their positions, but not the distances. So, the distances as it is. See here you have D, D, and here also you have D, D. And what are the distances? P, Q and S, and here also P, Q and S. Is it right? Now, lambda A2. Lambda A2 can be given by, what is meant by lambda A2? Flux linkage of conductor A itself in this group containing 6 conductors for the second L by 3 distance, right? Now, it is 2 into 10 power minus 7 common. What is the current flowing through A? IA by 2. Current flowing through A dash is also IA by 2, right? So, IA by 2 into A to A distance is R dash. Next, what is A dash to A distance? This is a horizontal distance, and this horizontal distance is given as P. So, ln of 1 by P. Similarly, now we need to consider B and B dash. B to A distance, what is B to A distance? D. So, ln of 1 by D. Next, B dash to A distance. See, if this is horizontal and this is vertical distances, if they are not changing, the distance between C to A dash is same as the distance between B dash to A. What is the distance between C to A dash? Q. So, the distance between B dash to A is also Q. That is the reason why you got 1 by Q here. Next, third one. Third one is C and C dash. Now, what is the distance between C to A? Here we are getting all the distances from all the 6 conductors to the conductor A. We need to keep this in our mind. Now, IC by 2 ln of C to A distance. C to A distance is D. So, D. Next, C dash to A distance. C dash to A distance is Q. So, Q. Now, for the first 2 terms IA by 2 as common, and it is like ln of A plus ln of B. So, ln of AB. For the third and the fourth terms, you got IB by 2 as common. So, IB by 2 and ln of A and ln of P, ln of AB. Now, it is 1 by QD. Similarly, for the third one also, you will get 1 by QD. Now, this is the second equation. Now, what is this? This is the flux linkage of conductor A for the second L by 3 distance, for the second part of transposition cycle. Next, this is the third part, right? For the third part also, the distances will not change, but their positions change. Previously, here you have A, now it is moved to here. Previously, here you have C, now it is moved to here, and B here. Like that, these are the third positions in the third L by 3 distance. Now, Q, Q, S all will not change, right? Now, again, what is the distance from A to A? R dash. So, 1 by R dash. Now, what is the distance from A dash to A? The distance from A dash to A. See, when this D and this P, horizontal distance and the vertical distances are not changing, then the distance between B to B dash, here in this diagram, the distance between B to B dash is same as the distance between A to A dash. Now, what is the distance between B to B dash? S. So, the distance between A to A dash will also be S. Hence, I can write IA by 2 into ln of 1 by S plus IB by 2 into ln of 1 by P, because B to A dash. Okay. So, B to ln of 1 by P, 2D, it is correct. Okay, sorry. First I have written B dash distance from B dash to A. What is the distance from B dash to A? P. So, P. And what is the distance from B to A? 2D. So 2D. Similarly, what is the distance from C to A? C to A is D. So D. And what is the distance from C dash to A? This horizontal distance, this diagonal distance is same as Q. So Q. Now for the first and second terms, IA by 2 as common. I applied the formula of ln of A plus ln of B. So we will get ln of AB. For the third and fourth terms, IB by 2 as common, and it is ln of 1 by 2 dP. And for the fifth and sixth terms, IC by 2 as common, and it is ln of 1 by QD. Now this equation gives us the flux linkage of conductor A in a group containing these 6 conductors for the third transposition cycle. So consider it as third equation, right? So I have not written, means I am not writing the equations because it takes a lot of time. If we write the equations one by one, it takes a lot of time. That's why I have not written the equations. Just I am explaining how I have written these equations. Now, how can I find the flux linkage of A for if we have transposition done? We need to find the flux linkage for the first L by 3 distance, flux linkage for the second L by 3 distance, flux linkage for the third L by 3 distance, and we need to take the average of them, right? So I have written again the same expressions here. The reason why I have written again all these 3 expressions is you need to add all these expressions logically. Means if you write each and every equation separately and add each and every term, you will get totally 9 terms, first 9 terms, right? So it will become a big expression. If you add the equations in a smart way, then it will reduces your effort, right? See, for all the terms, what is common? 2 into 10 power minus 7 is common. Here what we need to do is, we need to add lambda A1 plus lambda A2 plus lambda A3. Is it right? So for all the terms, 2 into 10 power minus 7 as common. So that is the reason why I have written 2, sorry, here I made a mistake. Let me change this. It is 2 into 10 power minus 7. Okay, 2 into, here also, 2 into 10 power minus 7 as common. Next, in addition to that, what is common? By 3. So that is the reason why I have written directly 2 into 10 power minus 7 by 3 separately. Now, if you see the first term in each of the 3 equations, first term is IA by 2, IA by 2, IA by 2, right? And it is like ln of A plus ln of B plus ln of C. So ln of A into ln of A, B, C. Okay, what is the formula which we can use to add all these natural logarithms? Ln of A plus ln of B plus ln of C is equal to ln of A, B, C. Is it right? Now in place of A, you have this entire term. In place of B, you have this entire term. In place of C, you have this entire term. Now I have written directly IA by 2 as common, ln of, what is A? 1 by SR dash. What is B? 1 by PR dash. What is C? 1 by SR dash again. So 1 by SR dash, PR dash, SR dash plus, next, now consider here, similar, you can apply the same formula here also. Now it will become A and it will become B, and you can consider this as C, A, B, C. If you observe the second and third terms for each and every equation, you have one natural logarithms as common. See, 2 terms with QD and one term with 2dP. Here also 2 terms with QD and one term with 2dP. So the natural logarithm will be same when you apply this formula for this second terms, and for also third terms when you apply this formula, you will get the term inside the natural logarithm as same. What is that term? It is 1 by 2 dp into qd into qd. Here also you have qd, 2 dp. As this term is common for both the things, both the second and third terms, I am directly writing it as IB plus IC by 2. So, I can simply write it as IB plus IC by 2 ln of 1 by QD into 2 dP. Is it right? 2 dP. Now, apply this condition of balanced system. Sum of all the currents must be equal to 0. From this I can write IB plus IC as minus IA. So, now in place of this, now in place of IB plus IC, what I can write? Minus IA. Now when I want to replace this minus IA with plus, what I can do? I can interchange the numerator and denominator inside the natural logarithm. Is it right? Now when you interchange the numerator and denominator, this term will go to the numerator and 1 will come to the denominator and it will become plus. Now for the second and for the first and second terms, you have IA by 2 as common. So I have taken again IA by 2 as another term which is common. Now what is the term which I can get in the numerator? Q times D, Q times T, 2 times dP. So you have D cube, is it right? Q square P do 2. This will be in the numerator, and in the denominator what you will get? R dash whole cube S square P, S square P, and what you will get? P and P gets cancelled. So finally you will get lambda A. Okay, let me take the highlighter. You will get lambda A as 2 into 10 power minus 7 by 3. Okay, let me cancel these two also, so that the burden will get reduced further. Now what you will get? You will get lambda A as IA by 3 into 10 power minus 7 ln of 2 d cube q square divided with r dash whole cube s square, r dash whole cube s square. Okay. Now what is this? This is the value of flux linkage of conductor A, which is expressed in Weber turns per meter. Now how can I find the inductance? This is the flux linkage actually. How can I find the inductance? Inductance LA is equal to lambda A by the current. Current flowing through the conductor A is IA by 2, and the current flowing through the conductor A dash is also IA by 2. So we will get IA by 2 as it is. Now it is equal to what you have as lambda A? IA by 3 into 10 power minus 7. So IA into 10 power minus 7 by 3 into, when you send this to numerator, you will get 2 by IA. Is it right? 2 by IA into ln of 2d cube q square r dash whole cube s square. Okay. 2d cube q square r dash whole cube s square, Henry per meter per conductor. It is not the inductance per phase. Now cancel out the terms IA and IA. Finally what you will get? You will get LA as 2 by 3 into 10 power minus 7 into ln of 2d cube q square r dash whole cube s square. But what I need is actually inductance per phase. Inductance per phase you can find by using the similar method. You can by using the same analytical method, you can find inductance of A dash conductor also. So you will get that A dash and A will be same and it is equal to L, right? In that case, what is inductance of A phase? Inductance of A phase, let me write like this. Inductance of A phase is L by 2. Is it right or not? Is it right or not? Because when you have two inductors of equal value L connected in parallel, now the equivalent inductance is the half of any one of the inductance. Now LA phase is equal to L by 2 and it is given by 1 by 2 I am writing separately into 2 by 3 into 10 power minus 7 into ln of 2 d cube q square divided with r dash whole cube s square Henry per meter per phase. Now it is a inductance per phase. 2 gets cancelled. So finally, let me modify this equation in a simple way. You will get 1 by 3 here, right? If I want to send 1 by 3 to here, I can write this as power 1 by 3. Power 1 by 3 can be written as LA. Finally, you will get 1 into 10 power minus 7. Please don't memorize anything while you are studying. Please don't memorize all these things. It depends upon the distances, means the vertical distance and the horizontal distance as well as the diagonal distances. You will get this answer when you use the means the mathematical analysis. What we are doing is very important and it is common to everything. If you observe, it is common to everything. So it is not difficult to understand, because first you need to find the flux linkage of one conductor in a group of 6 conductors for each and every part of transposition cycle, and you take the average of that, so that you will get the flux linkage of that particular conductor. From that find the flux, from that find the inductance of that particular conductor. If you know the inductance of conductor, you can automatically find the inductance per phase. Okay. So when you have 1 by 3 here as coefficient of natural logarithm, you can write it as the power of the term inside the natural logarithm. When you have power 1 by 3 here, you will get it as 2 power 1 by 3 and d cube into 1 by 3 is d. So 2 power 1 by 3 d q power 2 by 3 divided with r dash s power 2 by 3. S power 2 by 3. So this is the thing which you need to keep in your mind. Okay. So the unit is Henry per meter per phase. In this way, you can find the inductance of a unsymmetrical double circuit line in a vertical fashion using flux linkage method, right? Now it is your turn. Is it right? Now it is your turn to find the flux linkage, inductance of A phase using GMD and GMR method. Okay, you need to prove the same equation. You need to get the same equation, right? Now let me draw the diagram again for your sake, so that Now we will find the same inductance using GMD and GMR method. Why I am giving this method again? Because in numerical problems it is not possible to do everything by using flux linkage method. So in that case you need to go for GMD and GMR method, whatever may be the distances. So don't bother about these distances D, Q, S, R, R dash, okay. So for each and every problem there will be different distance. You need to keep that in your mind. So actually the vertical arrangement looks like this, is it right? Now what is this? We have assumed this as A and this as B and this as C, and this is A dash, B dash and C dash. What is this distance we have assumed? This distance we have assumed as P, and the first diagonal distance Q, the smallest diagonal distance Q, the largest diagonal distance is S, and the vertical distance between the conductors, this is D and this is also D, right? Now what is the formula which we can use to solve or to find the inductance using GMD and GMR method? L per phase, okay, keep in your mind, inductance per phase can be used, can be determined by using this simple formula, 2 into 10 power minus 7 into ln of dm equivalent by ds equivalent, right, Henry per meter per phase. Now what is dm equivalent? Dm equivalent is nothing but equivalent GMD. Dm equivalent is equivalent GMD. So equivalent GMD is nothing but cubed root of, is it right? Equivalent GMD is nothing but cubed root of GMD between AB, GMD between BC and GMD between CA. Similarly, how can you find DS equivalent? DS equivalent is cubed root of GMR of A phase, GMR of B phase and GMR of C phase. First let me find, see, in GMD and GMR method you can have only one part of the transposition cycle, no need to go for 3 parts. This is the advantage, right? You can take the diagram as it is given in the example or numerical problem, whatever it may be. Now how can I find the geometric mean distance between A, B? First, A phase contains how many conductors? 2 conductors, A and A dash. B phase contains how many conductors? 2 conductors, B and B dash, right? Now in finding the GMD between AB, we need to consider A phase as one side and B phase as another side. In case of composite conductors, when we are studying the inductance of composite conductors, we have considered 2 sides, X side and Y side. X side has m number of conductors or n number of conductors and Y side has m number of conductors, and we got that GMD as mnth root of mn distances. Here also we need to consider A phase as one side, B phase as another side, right? And if you observe here, how many conductors here? 2 conductors. So n value is equal to 2. And how many conductors here? 2 conductors. So m value is also 2. Now GMD is nothing but mnth root of mn distances. GMD is nothing but mnth root of mn distances. Now what is mnth root? Mnth root is nothing but 4th root, and how many distances you will get? 4 distances. 4th root of 4 distances. Now what is dm AB? What are the 4 distances you need to know? So 4th root of, what are the 4 distances? One distance from A to B, another distance from A to B dash. Now A is completed. Next B, one distance from A dash to B, the fourth distance from A dash to B dash, right? So A to B, A to B dash, A dash to B, A dash to B dash. Simple, very, very simple. Now it is fourth root of one distance from A to B. So A to B distance is D. So D into A to B dash. What is A to B dash distance? Q. So Q. A dash to B distance. A dash to B. So this is the smallest diagonal distance. A dash to B distance is also same as B dash to A distance, which we observe in diagram. So you will get Q again into, now what is A dash to B dash distance? A dash to B dash distance is same as C to B distance, which is D. Now it is D. What you will get now? It is D square Q square whole power 1 by 4. Now you will get D power 1 by 2 Q power 1 by 2. This is the value of DMAB. Okay. Now DMBC. DMBC is also fourth root of 4 distances. Why fourth root of 4 distances? B phase contains 2 conductors. What are the 2 conductors? B and B dash. C phase also contains 2 conductors, C and C dash. So now this value is N and this value is M. Now mnth root means 4. Fourth root now 4 distances. Right? What are the 4 distances? Now what are the 4 distances? Please do this. What are the 4 distances? D, B to C, D, B to C dash. B completed. Next go to B dash. So B dash to C, D, B dash to C dash. Now it is fourth root of, what is B to C distance? B to C distance is D. So D into B to C dash, B to C dash. It is the smallest diagonal. So Q into B dash to C, B dash to C. Again it is smallest diagonal. So Q and B dash to C dash. B dash to C dash distance is same as B to A distance. So it is again D. Finally you will get the same value as DMAB. So D power 1 by 2, Q power 1 by 2. Next go for the third. DMCA is also fourth root of 4 distances. What are the 4 distances? D C to A, D C to A dash, D C dash to A, D C dash to A dash, and it is equal to fourth root of C to A. C to A distance is 2 times D. So 2 times D into C to A dash. C to A dash. C to A dash distance is P. It is the horizontal distance which is common. And C dash to A. C dash to A, again it is P into C dash to A dash. C dash to A dash 2 times D. Right. Now finally what you will get? 2 into 2 4. D into D, D square. P into P, P square. Whole power 1 by 4. 4 can be written as 2 square. 2 square whole power 1 by 4 is 2 square whole power 1 by 4 is 2 power 1 by 2. So 2 power 1 by 2, D power 1 by 2 and P power 1 by 2. Okay. Now we can find DM equivalent. Now DM equivalent is nothing but cubed root of DMAB into DMBC into DMCA, and now it is given by cubed root of, what is the first term? D power 1 by 2, Q power 1 by 2. So D power 1 by 2, Q power 1 by 2. Second term is also same. So d power 1 by 2, q power 1 by 2. So these are the product of the distances. Keep in mind, right? 2 power 1 by 2, d power 1 by 2, p power 1 by 2 under the cubed root, right? So it is also equal to dmab, right? Now it is equal to cubed root of d power 1 by 2, d power 1 by 2, d power 1 by 2. So d power 3 by 2. Q power 1 by 2, q power 1 by 2. So q and p power 1 by 2. In addition to that, you also have 2 power 1 by 2. When you apply 1 by 3 here, because it is power 1 by 3, you will get d power 1 by 2, q power 1 by 3, small p power 1 by 2 whole power 1 by 3 is 1 by 6 and 2 power 1 by 6. So this is the value of dm equivalent, right? Now can we move to the next one, which is the ds equivalent? Now find ds equivalent. Let me start from here. So ds equivalent is nothing but cubed root of dsa into dsb into dsc. Now what is dsa? dsa is nothing but GMR of geometric mean radius of a phase, and it is given by n squared root of n square distances. GMR is always n squared root of n square distances. GMD is nothing but mnth root of mn distances. Now what is n? N is nothing but the number of conductors in that particular phase. Okay, so here A phase has two conductors, one is A and A dash. B phase also has two conductors, B and B dash. C phase is also has two conductors, B and B dash. So DSA is same as DSA is fourth root of four distances. DSB as well as DSC all are fourth root of four distances. Okay, fourth root of four distances, because n value is equal to 2. Now what are the four distances? Fourth root of four distances are distance between the conductors of the same phase. Conductors are A and A dash. So the distances are, one is the self distance A to A, next distance is A to A dash. Third one is another self distance A dash to A dash. Fourth one is A dash to A. Now what is this value? It is fourth root of A to A is R dash. We know this already. And A to A dash, if you observe from the diagram, it is S. It is S. And A dash to A dash. What is A dash to A dash? It is also R dash. And A dash to A dash, A dash to A is S. So it is R dash whole square, S square whole power 1 by 4. Now what you will get? R dash power 1 by 2, S power 1 by 2. This is not 1, okay, it is R dash. This is DSA. Similarly find DSB. DSB is also fourth root of four distances. Now what are the four distances? It is fourth root of DBB, DBB dash, next DB dash B dash, next DB dash to B. B to B, B dash to B dash, all are self distances, right? Self distances are R dash. Now R dash into, what is B to B dash distance? P. So P into again R dash into P. So you will get R dash whole square, P square whole power 1 by 4. Now DSB is equal to R dash whole power 1 by 2, P power 1 by 2. This is DSB and this is DSA. And if you observe the diagram, the distance between A to A dash is S, so that the distance between C to C dash, they are also at the corners of largest diagonal. So A to A dash distance is S. So C to C dash distance is also S. In that case, you will get DSA as DSC, which is the value R dash power 1 by 2 S power 1 by 2. Now, what is DS equivalent? DS equivalent is cubed root of DSA is R dash power 1 by 2 S power 1 by 2, and DSB is again R dash power 1 by 2 P power 1 by 2. Next, DSC is also same as DSA, so R dash power 1 by 2 S power 1 by 2. So finally you will get cubed root of 1 by 2 1 by 2 1 by 2 power 3 by 2. So R dash whole power 3 by 2, and S power 1 by 2 S power 1 by 2. So you will get S, and here you will get P power 1 by 2. Now by applying this cubed root, you will get DS equivalent as R dash power 3 by 2 into 1 by 3, because power 1 by 3 can be taken as into 1 by 3. So 3 by 2 into 1 by 3 is 1 by 2, I think so. So we will get R dash power 1 by 2 and S whole power 1 by 3. Cubed root means power 1 by 3, and P power 1 by 2 power 1 by 3 is 1 by 6. So this is the value of DS equivalent. Equivalent GMR is this value. Similarly, equivalent GMD is this value. Okay. Now substitute these two in final formulae. The generalized formula, which is L per phase is equal to 2 into 10 power minus 7 into ln of dm equivalent by ds equivalent Henry per meter per phase. Now it is 2 into 10 power minus 7 into ln of, what is dm equivalent? Dm equivalent is what is dm equivalent? Dm equivalent is this one, d power 1 by 2 q power 1 by 3. So d power 1 by 2 q power 1 by 3 p power 1 by 6 and 2 power 1 by 6 divided with dqp completed. So dqp. Next, ds equivalent. What is ds equivalent? R dash power 1 by 2 s power 1 by 3. So r dash power 1 by 2 s power 1 by 3 and p power 1 by 6 Henry per meter per phase, inductance per phase. Now in the numerator you have p power 1 by 6, in the denominator you have p power 1 by 6, both will get cancelled, right? Send this 2 to here. If you send this 2 to here, it will become power 2. Now it will become 1 into 10 power minus 7 into ln of 2 power 1 by 6 d power 1 by 2 q power 1 by 3 divided with r dash power 1 by 2 s power 1 by 3 whole power 2, because it is multiplied with 2. When you send it inside the natural logarithm, it will become power 2. So finally you will get 1 into 10 power minus 7 into ln of 1 by 6 2. So 2 by 6. So you will get 2 by 6 as 1 by 3. So 2 power 1 by 3, 2 by 2, you will get 1. So d power 1 means d and q power 2 by 3 directly divided with, so 2 by 2, you will get 1. So r dash into s power 2 by 3. It is inductance per phase of an unsymmetrical double circuit line arranged in a vertical fashion with the vertical distance as d, right? With the vertical distance as d, and the smallest diagonal distance is q and the largest diagonal distance is s with the radius as r. So now what is r dash here? R dash is nothing but, okay, r dash is equal to 0.7788 times r. Now let me copy this. Now see the expression. So this is the expression which we derived, okay, 1 into 10 power minus 7, 1 into 10 power minus 7, ln of ln 2 power 1 by 3, 2 power 1 by 3, d, q power 2 by 3, q power 2 by 3, r dash, s power 2 by 3, s power 2 by 3. Okay, so the first thing is the flux linkage. If you observe here, this is the term which we obtained by using GMD and GMR method, and this is the term which we obtained by using flux linkage method. You got the same expressions by using two methods, right? But this method is helpful for any type of configurations. In order to solve the numerical problems, you need to apply only GMD and GMR method, because flux linkage method is difficult to apply for each and every problem. It is difficult to apply flux linkage method. So you can go for GMD and GMR method only for numerical problems. But you need to understand how can we apply GMD and GMR method. Is it right? Here there is no need to go for 3 transposition cycles, but here you need to do transposition when it is unsymmetrical. When it is symmetrical, no need to go for transposition. So you can apply this method both for symmetrical as well as unsymmetrical. This is the generalized formula which can be used everywhere.